All right, welcome everybody. I'm Gordon Rosner, your president. Here's the agenda that's been up for a few minutes. We'll of course have the usual welcome and the introductions. Got some new club news for you this time. Member presentation will be by Bob, and he'll do the Society for Astronomical Sciences Symposium with a couple other cool stuff too that he'll add in there for us. In our main presentation, Richard Hedrick, CEO of PlaneWave's instrument. So all those telescopes that we're jealous of, we have Richard with us to explain his company. And as usual, everyone, welcome, live long and prosper. I always put this up, and it's only because to let people know that this is the leadership team. This is who keeps the club running. And they've been busy this last month, and we'll get into why in the next couple slides. But down there in the lower left, remember, the most important member of the club is you. All right, so you're the one that comes on in, joins us during our monthly meetings, keeps the club going. Remember, our next EVAC meeting is on Friday, the 21st of May, so it's late that month. And our main presentation will be Dave Eicher, Astronomy Magazine's chief editor. And he'll be talking about Universe's star cities. So be sure not to miss that one. Club news. All right, line one. Greco is going to open for private star parties starting the 26th of April. The board of directors and leadership team, we've been discussing this and had a couple of meetings, online meetings, making sure that we're comfortable with this, what all the inputs that were needed to make a decision. Now, no public meetings are going to be happening, but Greco, we're doing the private star parties. Now, these events have been going on for years since Greco's been open, but since everything has been closed down in the past year, of course, these have been closed down also. But what we do is, of course, we're open to the public on Fridays and Saturday evenings, so anyone can come and join us a good time at Greco, which is our observatory. But Sunday through Thursday, we have private viewings where families will ask, hey, can we come on in and spend an hour, hour and a half, and just kind of enjoy the sky? And so we offer that to people. Well, it's been discussions that are going on how do we dip our toes in the water, so to speak, as far as opening. I mean, we just don't want to open up everything. So we thought Greco, what we'll do is at private parties, because there's only about 6 people, between 4 and 6 people that come. We can easily control the environment. We can see how things are going, get up a little bit of history, and it always, if it doesn't work out well, we can always cancel those on out. But the leadership team decided that, yes, that's a good thing to do. So we are opening our Greco Observatory for private viewings. And to schedule that, people will just go into our website, and on the Greco page, there's a link in there on how to schedule a private party. So, of course, those who show up, they have to sign a waiver, they must wear a mask, appropriate CDC guidelines will be followed. To make this decision, the leadership team had to get with our insurance company to make sure that they were okay with our plan. We had to get with the town of Gilbert to make sure that they were okay with our plan, which they were. And we had to get inputs from our board of directors on what they thought about this. So it was unanimous that let's do this. Let's open it up for private star parties only, starting on the 26th. And then the leadership team will evaluate. Claude Haynes, our observatory manager, will keep the leadership team involved and see if everything is going well, if there's any changes that we need to do. But remember, all other EVAC personal contact events still remain canceled. So meetings, public star parties, outreach events, they're all canceled until we can make decisions on them. And like it says at the bottom, we currently still don't know when that is going to happen. Now this is standard stuff. This has been up here for months now. Member presentations, if you're interested in giving a member presentation, get a hold of me, and certainly we can put you in there. Member articles, this is a new, a new thing that we've added a couple months now, is that if anyone has an article, instead of having a member presentation, if they want to write a short article, then send it on in. Send it on in to me, and we can on getting it included in our monthly newsletter. So please, if you want to be a published astronomy writer, join us and get your thoughts on paper and see if we can get you in the monthly newsletter. Remember that these monthly meetings are recorded, so there'll be a link in our website that you can go back and you can look at any of our monthly meetings, our Zoom meetings, and take a look. Our member presentation this time is by Bob Buchheim, and a lot of the EVAC folks will certainly recognize Bob and his observatory. He has a fabulous observatory on his house. Let's see, on it or next to it? I think it's kind of both. So some EVAC members and some SAC members helped him out, especially at the end when he was putting his dome on there. So we're fortunate that Bob's going to join us and talk about the Society for Astronomical Sciences, their symposium that's coming on up. So what I will do is I will hand it over to Bob right now.
Thank you very much, Gordon. Okay, am I sharing slides?
You're looking great.
Great. Thank you very much, and thank you for the audience letting me give a little spiel here. This is that backyard observatory that Gordon mentioned that was put together with the help of some generous folks at EVAC and at SAC. Thank you very much, guys. For 2 years now, this has been the biggest telescope in the neighborhood. But it's not anymore. One of my neighbors, literally just a couple of blocks away, finished construction of his house with an observatory built onto the garage, and it includes a 20-inch PlaneWave. Beautiful setup. But whether you have a fancy observatory like this, or you go out in the driveway with binoculars or naked eye to look at the stars, as an active observer, you know about the amazing things that we can see and measure in the night sky. And one of the ways to organize those objects and phenomena that we see is to describe them along 3 dimensions. First, some of them are faint and some of them are bright. Some of them are invariant. They don't change. You know, when you look at M51 tonight, what you see is pretty much the same thing that Herschel saw 200 years ago. Unless what you see is a supernova, which flashes and then fades away over a few months. Regarding the part that doesn't change, a single well-done measurement will capture pretty much everything that you need to see about that object. But to understand the changing part, like that supernova, you need to watch it every night, what astronomers would call time series observations. And among those things that change on time scales that are visible to human beings, some of them require observation every few minutes, every few hours. Some of them require observation occasionally over years and decades. So the observing cadence that the object or phenomenon requires is an important parameter. Now, most of the instruments at big professional observatories are optimized to look at faint objects. And those instruments are badly oversubscribed. There are more observations that researchers want to do than there is time in the night. And what that means is their sweet spot is down here. Relatively infrequent but very precise measurements of faint objects. But there are quite a few objects and phenomena that are relatively bright and for which researchers need observations and measurements. And those are things like asteroid rotation periods and the shape models that can be derived from them. Transient events like nova or asteroid occultations, Wayne. A variety of forms of stellar variability. And even the orbital motion of binary stars, visual binaries, need to be touched every 5 or 10 years to be able to determine their orbital parameters. Now, what do I mean by bright? Consider the Sloan Digital Sky Survey and Pan-STARRS. The brightest stars that they can make accurate photometry measurements on is about 14th magnitude. Brighter than that, their instruments saturate. Now, that bright limit that they face is just about the same as our faint limiting magnitude. Bigger scopes like Gemini, of course, and the upcoming LSST Rubin Observatory have even fainter bright limits. And that means not just for our own personal observing, but in terms of scientific measurement, we own the bright sky. And whereas the big professional observatories are oversubscribed, we can squander our observing time on whatever interests and entertains us. We can spend all night, every night for a month on a single object. We can partner with each other around the world and keep an object under 24-hour surveillance if that's what it requires. And that means there are projects that we can do in our backyards that researchers need the data on, and those things are not practical to do at the big professional observatories. So the message is there is a role for people like us in astronomical research. For example, this is a AAVSO, American Association for Variable Star Observers, light curve, a plot of brightness versus time of a particular variable star Chi Cygni. Its changing brightness is readily observed and measured in a backyard scale telescope, and the astronomers rely on people like us to contribute the data points that go into a light curve like this one that characterizes the pulsations of this star. And it turns out that a small telescope with a spectrograph attached can actually watch the physical state of this star change as it goes through its pulsation. You know, look at the way some of those spectral lines change as you go from May to July to August to November. Some come and go, some shrink and expand, betraying temperature and other phenomena on the visible surface of that star. Several months ago, I got a call. I think it was Claude Haynes first got the call from this girl, a high school girl in Gilbert, who wanted to do a project on exoplanets. He passed it off to Woody Sims, who called me, and she used my backyard observatory to do her science fair project, making a transit light curve of this exoplanet, WASP 33b. It's about an 8th magnitude star, so it's bright, and we're looking for a brightness change as shown in the blue dots that's a little more than a 1% change in brightness. So the trick is very precise photometry and very precise timing of it. Well, with 4 transit observations on 4 separate nights, she was able to do 2 things. She updated the orbital ephemeris of this exoplanet, and she got 3rd place at the state science fair. So, very well done. Tom Palakis, whom most of you know, spends his evenings, some of his evenings, staring at asteroids. And each one of these light curves is adding a new nugget of knowledge about the solar system by determining orbital rotation periods. In this case, Tom is the first to have measured the rotation period of this asteroid. So if you'd like to learn about projects like these and other projects that you can participate in, then you are the target audience for the annual symposium of the Society for Astronomical Sciences. This year we'll be meeting online. We just couldn't bring ourselves to go in person this year. Too much uncertainty about the ability of hotels to honor contracts and what the local legal authorities are going to do. That means bad news, we won't be able to get together in the bar after the talks. But the good news is it will be easy to participate. You'll learn about a variety of avenues for small telescope research opportunities. You'll hear from the results of projects that people have been doing over the last several years. We're trying a unique format for this kind of a meeting. Rather than you come in and listen to live presentations, the presentations will be pre-recorded and available to you about a week before the meeting on video. And then the purpose of the live gatherings online is to have Q&A with the presenters and extended discussion among the audience. We think that this format will enable us to be a lot more interactive and get a lot more discussion going among both the presenters and the audience. So mid-June, registration information is on the SAS website, socastrosci.org. Look forward to seeing you there. Also, since Rick Hedrick is our main speaker tonight, let me give a shout out. PlaneWave Instruments has been a long-time supporter of small telescope astronomical research, amateur research activities, and for years a loyal sponsor of SAS. So thank you, Rick. We couldn't have done it without you. If you all have any questions, I think most of you know how to get a hold of me, but check out the schedule and join us at SAS this year. Thank you very much. That concludes my prepared remarks.
So just a reminder, if anyone has questions, please post them in the Q&A so we can notice them. Or if you think of a question later for Bob, just put it up there and we'll get to it later.
All right, thank you, Bob. Thank you. And now we'll move on to our main presentation, which Tom will introduce Rick Hedrick for us from PlaneWave. So, Tom, take it away, you and Rick.
Okay, well, thank you, Rick, for having agreed to spend some of your time talking to us, and it's my pleasure to introduce you very simply as simply the president, CEO, and co-founder of PlaneWave. What more can I say? We're all very excited to hear you talk about the goings on of PlaneWave. I'll just be quiet and let you talk. All right, thanks.
Okay. Yeah, thank you. Thank you for having me here. I'd like to share my screen. Yeah, I have the ability to do that, looks like. Yeah, here we go. All right. And if for some reason internet's cutting out or something, please let me know. Let me get this going here. Yeah, so I'm Rick Hedrick from PlaneWave. And this is a little, I have kind of three different topics I'm talking about, which will be kind of a history of PlaneWave, a little bit of showing you around the factory and what we do there, so some of our processes, and then also talk about a new product that we have coming out. So PlaneWave really kind of started in a sense at El Camino College. So this is a community college that I went to back in 89, 90, 91, something like that. And they had a 16-inch Celestron telescope in their main observatory. And then they had, move this to the side. And then they also had a nice observing deck, and they had, they first had Meade telescopes and eventually moved over to Celestron telescopes. So that's kind of where I got acquainted with astronomy. In fact, I got involved there. I met a professor that I really was inspired by. He was a astronomer at JPL, full-time astronomer at JPL, and a full-time professor at El Camino College. And I didn't even have his class. I just heard him give a talk at the science club meeting. And so I went in and talked to him, and I said, hey, I'd like to do an independent study. He said, you're doing interesting things. And he said, well, you could do a study on globular clusters. You could do a study on, irregular galaxies. He says, or you could try astrophotography. And I'm like, yeah, I want to try that. So, I ended up doing photography with film with that Celestron C18, doing planets at first. And then I borrowed this 10-inch telescope from the class that was homemade, donated to the class. And so I would take this out and do astrophotography. And this little telescope here is a real cool, rare thing. It's a 6-inch Celestron Pacific F20 Schmidt-Cassegrain. And that was the guide scope for this 10-inch F5 Newtonian. And then while I was at El Camino getting into telescopes, I started working part-time at tech support at Celestron because I love telescopes. So I also here was taking out like an Ultima 8 and going out and doing astrophotography at the White Mountains. And here's good old-fashioned film, guiding for 45 minutes in a lit reticle eyepiece and finding out that, you really weren't quite focused, doing knife edge focusing. And but here's some images from those days. And then I would also go sometimes on a school night. It would just be such a beautiful night. I'd go up to the top of Mount Wilson. Here is Mount Wilson over here. Here's this big like valley right down here between where the hill that I'm on and the hill where Mount Wilson is. And here's Jupiter, and it's casting, it's reflecting in the fog there in the valley there. So it's kind of a neat shot. Here's Professor Hacking, Perry Hacking, and Stephen Lloyd, another professor at El Camino. Here we are observing out in San Pedro Martir in Baja California. This is a 20-inch telescope that Perry had. Here we are out in California observing with my 10-inch telescope that I was using. And then I went to Perry one day after we've been observing a lot and doing astrophotography and visual observing. And a friend of mine and I were talking about it'd be fun to make a telescope. And so I went to Perry and I said, hey, what if we started a telescope making class? And he said, well, telescopes are pretty hard. And he says, well, if you can get, 10 people to sign up, I'll see if the school will give us a place to work. So I went out and got 10 people to sign up. And, in 1991, we started the first telescope making class, and we all made 6-inch telescopes. And like I say, that class is still going there today. So, and now you get credit for the class at El Camino College. There's Perry working on his first 6-inch. And so, here's my first 6-inch telescope here on a little Celestron mount. And then later we made bigger telescopes. We made big Dobsonians, and we would go observing all the time. Every new moon we could go before we had kids and wives and everything. And then, after that, I went off to UCLA, and I was getting my degree there in physics, but I'd come back weekends and work on telescopes for fun at El Camino College. And then by 1998, we decided, hey, let's make a really big telescope. Let's make a And we decided to make a 42-inch telescope because the biggest that we saw that an amateur had made at that point was a 41. So this was one bigger. And it was also the answer to the life of the universe and everything, if you read those books. We were going to design a big hyperbolic Newtonian and use a wind corrector. So here was the paper design we'd come up with. And, but the problem is the ladder is really high. Even at f4.5, you know, it was, you know, it's a very tall ladder and not an ideal situation. And our design parameter was to cover the 31 millimeter Nagler eyepiece field of view with pinpoint stars. That's what we were shooting for. So then we ordered a 42-inch mirror blank in 1998 from Wangsness. You know, 6 of us put some money, or 5 of us put money together to have him make the mirror, but he was giving us a really good price, so we were low on the priority. So it took quite a few years to get it. But in the meantime, you know, we started, you know, working our design and continue making other telescopes. And then 1999, a gentleman, Dave Rowe, had heard about the telescope making class, and he came in and kind of looked at the big project we were working on, was really interested, and said, and he kept asking us questions. Well, if you had the, you know, how far away from the tertiary mirror would you have the focal plane? You know, what kind of field of view are you looking at? What kind of, and he went home, was working on, he had a design that he had come up with called a CDK, or at least we call it that now. It wasn't called that yet. But it was a design that had a spherical secondary mirror. It had a nice wide corrected field of view with pinpoint stars across the field. And if we put like a tertiary mirror here, we could, you know, light would come in here, hit the primary, hit the secondary, hit tertiary, and it wouldn't be a very tall telescope, and it would fill the 31 millimeter Nagler eyepiece. So, you know, we're like, you know, we liked the idea. We changed our design to that because we had a mirror on order, but we still didn't have it yet. So our design was still up in the air. So this design had lenses about here, and the M3 and the M2 and the primary mirror. So during that time, we started making the lenses and started making the secondary mirror while we were waiting for the primary. And then in 2002, the primary mirror finally arrived. So Perry went to pick it up in Arizona in the back of his truck, and there she is. So we started grinding, and here's the telescope making class. Here's Joe Haberman, who's one of the founders of PlaneWave. Here's Manisha Gupta, who's an engineer at Celestron. Don Kwok is a guy who made more mirrors than anybody, but never turned them into telescopes. He just made mirrors. And he was also an aerospace engineer. And then here we are, I think, like doing the first grind. So, and it was quite a sound. You can imagine if you've ever heard grinding mirrors, a big one like this is really loud. We even would grind 2 people at the same time. There's Joe measuring. Here we are doing some polishing, doing figure. Let's see what I say here. Yeah. Anyway, so we're polishing, turning the edge down a little bit. Here's our test setup for the mirror. Here's Jason Fournier, one of the other founders of PlaneWave, doing Foucault testing. Here's kind of the software that Dave wrote that we would use to examine the Foucault data, an old DOS program. And then when we were doing the initial grinding, we did not rotate the mirror as much as we should have, so we got astigmatism built into it. So here we are having to polish again and try and polish off the astigmatism we put into the mirror, which we eventually did, but it was a lot of work, a lot of spinning that darn mirror. Here was the secondary mirror that we made. And in 2009, we had first light, and it was a great telescope. And I think there's even, in 2010, here it is under dark skies. We even brought it to RTMC one year. And so, you know, it's looking through the 42-inch telescope, M51 was incredible. It's amazing. Some objects, as you probably know through big telescopes, it's this giant difference, and other objects make very little difference when you're looking at them. So it's very neat to find the objects that just really jumped out at you. But meanwhile, let's backtrack to 2002. So Dave and I would be working, polishing, and we would talk about telescopes all day. And at this point, I was probably at Celestron now. So when I graduated from UCLA, I went and got a job at Celestron, and I ended up heading up the engineering department and the product development there. So at this point, CCD chips are starting to get big and become very relevant. And we're like, what would be, this CDK would be an excellent telescope for imaging because it has pinpoint stars and a flat field. And a secondary mirror, it's a sphere, so it's very easy to align. And I think this is about the point in time when we had bought Celestron. So me and a couple of Joe Lapika, a couple of the last presidents of Celestron had bought Celestron. And so we were looking for a flagship for Celestron. So in 2003, we designed a 18-inch CDK. So that was our first CDK. This is me, Joe Lapika. Here's Joe Haverman. So Joe had a day job, and I hired him away from day job to be the optician for the big telescopes. Because in the telescope making class, Joe was the guy, and we all liked making optics and designing telescopes, but Joe was the one who really liked fighting a piece of glass. I mean, he just made one after another and turned them into telescopes. And even for a while had a little side business making mirrors for people. So he really loved making mirrors. And so he's our master optician. And this is Chris Paul, who's one of the engineers also at Celestron, and Bob, the mechanical engineer at Celestron. So then we updated the design to be a 20-inch, and we decided the 18, for certain reasons, we thought 20 would be better. We made a mount, made the 20, and that's about May 2005, the C20. And we sold 2 of them. And then Celestron got not distracted. We got into a mass market product called the Sky Scout, and it took a lot of engineering to get the Sky Scout going. And we also realized that the C20 took a more technical staff than Celestron was really prepared to have. But I thought, this product it's got to hit the market. The CDK is a very important. I was pretty passionate about it. So yada yada yada. I made a deal with Celestron. We had sold Celestron, and I stayed there a year and a half, and then I left and started PlaneWave. And I bought all the inventory. I bought the mechanical drawings we had done. The design was, mine and people from telescope making class anyway, so that wasn't an issue. And so we started PlaneWave in 2006. And so here's Joe and I. We left Celestron to start it. But the truth is, these are the 4 people that actually were the founders of Celestron. You had Joe Haverman, Jason Fournier, myself, and Corey Lee. So Corey Lee is now the president of Celestron, but he's also, he's a mechanical engineer. He was a mechanical engineer at Celestron before that. And he designed the 12.5 for PlaneWave. So when you look at the 12.5, if you ever see Corey, say, hey, I heard you designed the 12.5 for PlaneWave. He did. That's when he was still one of the owners of PlaneWave. Later on, we bought him out because he decided to stay. Jason decided to come to PlaneWave, and but we're still great friends. So meanwhile, 2006, we were still working on this, the Big 42, and Dave and I started talking about what's the perfect telescope. We designed the 20, right? And we had that out, and we designed a mount. But our goal was always to make, there's all these features you wish existed. And so we were always adding features and adding to our dream list of the things that we wanted telescopes to do. And we had kind of come to the conclusion that the perfect mount would be a direct drive mount because it doesn't have any gears. There's no So the gears wear out, they have periodic error, they have backlash. Direct drive doesn't have any of those things. So we were kind of coming up with the concept of what's the perfect telescope. And then at RTMC 2007, I met Russ Genet. Russ Genet wrote the telescope control book with Mark Trueblood. And that was a book when I was at Celestron, and we designed the Next Star series and all that. I was reading, we were all the engineers were reading his book on that, as well as some others. So when I saw him walk into our booth at RTMC, I'm like, Russ Genet, you know, God, come on in here. So we went to dinner and we talked, and then we met, well, a big dinner, and we're talking about perfect telescope, and he had been talking about similar ideas. So we kind of, Russ Genet pulls groups together, and he pulled a group together called the Altaz Initiative. And it's a big, and we would meet regularly and talk about the perfect telescopes and what would be, you know, we figured Altaz was the way of the future for even amateur telescopes. And here you can see, here's Tom Johnson, who was the original founder of Celestron. He went to one of the meetings, and Greg Johnson, his son. Dan Gray, who did electronics for some of PlaneWave's products, and he's got you know, his own company that sells great electronics for telescopes, and also was working closely with Dave on the Dave Rowe right here for the original direct drive motor concepts. So these are some of the meetings we had, and it was also involved with Cal Poly in San Luis Obispo. So Cal Poly had some students that built an 18-inch telescope, and I think we provided the optics. I know I can see one of our truss poles are here, and this was the first motor that we had built, and that's on their mount there. So they built an 18-inch direct drive with Dan Gray's electronics. And then by 2010, we released the CDK 700, which is a 0.7 meter Altaz CDK telescope with dual Naismith ports. So dual Naismith means, you know, the light comes in the front, hits the mirror, hits the secondary, hits a third mirror, tertiary mirror, and comes out the side here. But you can rotate the tertiary mirror and have the light come out the other side too. So like for a college, you could have an eyepiece on one side and have your expensive camera on the other side, and you don't have to have students taking off this camera. Or you can have other groups that you know, put a spectrograph on one side and a camera on the other side. In fact, yeah, that's right here, Minerva. They have 5 of our CDK 700s on the top of Mount Hopkins, and they do exactly that. They do spectroscopy on one side, and they do photometry on the other side for exoplanets. Here's sort of an example of the CDK 700 doing fast acquisition with just like a webcam. So it's a 3 arc-minute by 2 arc-minute field of view. Is out in the back of PlaneWave when we were in Southern California. So anyways, you can see that. So direct drive, cool. And then then we worked on the 1 meter, which was a giant project, and I'm just jumping ahead to when it's done. And here's Russ Genet visiting us to check out the 1 meter, and Dave Rowe and myself. And so in 2017, we released the PW1000, and we've got like 17, 18 of them out installed right now out in the field. So we've been selling these like, you know, like no one else. This is the first 1 meter telescope that was sort of an off-the-shelf product with a price on the website, and very high performing. You know, it's got lightweighted primary mirror. Maybe I have a picture of that. Let's see. Yeah, I do. Okay. So he has lightweighted primary mirror. So the primary mirror here, 1 meter, only weighs 120 pounds. When, you know, any of the competitors to us, theirs weigh in the order of like 600 pounds for their primary mirror. Then we decided to take the technology down to the direct drive technology down to the L mount. We wanted to have that same cool direct drive high performance and be able to offer it to more people. And so here we are tracking satellites and doing fast acquisition with an L mount and a 17. And these happen to be satellites. That's why you're seeing all the stars moving in the background. I'll do a couple more of these. And it's amazing because you can actually see the mount moving in some of the, I mean, it's moving like at some point you get to like 2-3 degrees per second. This one was behind a cloud. Anyways. So we took that concept of the direct drive and brought it down to hold our 17s and our 20s, and here's sort of the kind of complete product line. The only one missing here is the 12.5. But so you can see, this is sort of, first, this has, anyways, and here's a couple examples of astrophotos taken with a couple of our telescopes. Hello, there you are. That's a great mosaic of Andromeda by Martin Pugh. And so that's the end of my first, that's sort of a brief history of Celestron, of PlaneWave. And does anybody have any questions before I move to the next topic? And I'd like to know that people are actually out there.
There is one by Tony George. What are the blue pieces on the support struts?
Oh, what were the blue pieces you said? Those are, it's actually their clamps. They're just, so we've got ball ends on the ends of the support. And so we kind of clamp the balls in place. And the blue is just, we make them blue just as a pretty accent color. But it's really just a clamp to hold the ball ends. So.
See, then another one, Tom Plakis. Roughly how many of each aperture have been sold?
That's like, I think the 12.5s are probably 200 and something. 14s, which came out later, are on the order of probably just over 100. The 17s are 120-ish. 20-inch telescopes are probably around, they're over 100 also. And I think that, I'm not sure how many the 24 are, but the 700, we have about 45 of them out there. And like I said, the 1 meter is about 18 out there.
Okay. Yeah, I think we'd like to help your numbers go up. Let's see, another one, Rick Scott, are camera rotators standard with the telescopes?
Yeah, so with the CDK 700 and the 1 meter, they come standard with D-rotators. And the other ones, it's an option. So if you buy an L mount, you can mount it equatorially, where you don't need a D-rotator, although you may want one for framing a shot, finding guide stars or something. Or if you use it out as, then you'll definitely want to buy the rotator. But it is an accessory that comes with it. You pick if you want it or not.
Okay, and then another one, why did you move out of California, and where did you go, and why you selected the place you selected?
Well, that's a whole nother great story, but I'll just say quickly. We were in California. I had met Kevin Eyett, who is a mount designer, young man, and he a great designer and machinist. And so we started a company in Michigan where he lived. We did all our machining there. The first mount we designed is the Ascension 200, which I see is one of the other questions. It was sort of a mix of what we made at Celestron and Kevin Eyett's mount. Anyways, so we were in two places. We were in Michigan and we were in California, and we were growing. We had back orders we couldn't keep up with. California just made no sense to grow. Every time we're looking at buildings and looking at stuff, Michigan, and he's in Michigan. Michigan was the place to grow. And I flew out to Michigan. I'd fly out there multiple times because we had a shop there. but I flew out there looking at buildings, and I just was totally depressed because I thought, I don't want to live here because it's out in farmland and it's foreign to me. And yeah, I didn't want to live in Michigan, but I don't want to grow the company and not be with the company. And then one of the local politicians kept telling Kevin, go look in the city of Adrian. It's the little big town in, we're an hour from Toledo and an hour from Detroit, and 45 minutes from Ann Arbor. And when I saw this town, I fell in love with it. And we ended up buying 57 acres, an old school, PlaneWave did. And we've got, it's just a wonderful story. There's so many great things. We're going to build a 1-meter observatory on the campus. We have schoolhouses. We've got a gym. We've got a nonprofit wood shop that's on our land. We've got an art group that's on our land. I mean, it's gorgeous. And then you buy a house and it's big. And so I moved, and I'm a big believer in, in the area. And it's really wonderful to be here. So that's the answer. A little bit question.
Great. And I don't know if you're looking at that question, the one about the CDK24.
Yes.
Loves it and has a question about the change in focus with temperature.
Yeah, it was still a Pyrex mirror, I imagine, Tim, because we've changed. We don't even sell Pyrex anymore because they change temperature. They change focus. Even though Pyrex is pretty stable, in a remote observatory, the focus does shift and takes a while to settle down. So everything we sell now is fused silica. And that focus is much, much more stable. It costs a little more money, but it's much more stable. So focus does change, yes.
Okay, and then Tom Curry, were there any major obstacles to having a one-arm suspension for the scopes?
Well, we had to do a lot of FEA, finite element analysis and vibration analysis. And so, because you're holding with one arm, but the advantage is you can put different telescopes on it, sort of like a German equatorial, and you don't have to line up 2 forks. Whenever you have 2 forks, lining them up is a big deal, and because they don't really tend to line up, and especially weldments, when you weld it and and you bend it into shape, then you go ahead and you powder coat it where they heat it up, right? They go like this. And then you got to like bend them back, have all these adjustments. It's really difficult. We were trying to get this, try and get the price, as affordable as we can to get this great technology. So we just designed the forks really beefy.
Oh, interesting. Okay, thank you. And maybe related, why alt-az mounts?
Well, alt-az, especially when you get to the 700 and the 1 meter, to make those equatorial makes them extremely massive. And it's a completely different design. If you design it equatorially, this is why Keck and all these big telescopes are all alt-az, because, go look at Palomar, right? That's equatorial, and yet the telescope is dwarfed by the mount. So if you want to have, an affordable system, then alt-az is the only way to go. And it's easy today with computers because derotation is a very easy calculation, and it works very well. Now with the L mounts, we know those are small enough that you can go ahead and mount them equatorially or alt-az, and mostly we use them alt-az. So there's only some cases. I think with astrophotography, it's a little bit nicer to do equatorial because as your field is derotating, your spider vanes are rotating relative to the field. So you can have a fanned out look for for a series of images. So, but for science, it's, and even I've seen great astrophotography done alt-az too, but it's just a little bit more complicated. So anyways, perhaps I should jump on to kind of the little bit about the plant.
Sounds good.
Okay. So I'm still sharing, right? Let me see. Yes. Let's see if I can figure out how to get to the next. Dun, dun, dun. Okay, so let's start here. All right, so here I'll first start off with a little bit of just the process of, move that out of the way. Okay, the process of making a telescope. I'm going to kind of follow a primary mirror through the process and what we do at PlaneWave. So we get a mirror blank, and we get them out of fused silica. It's like fused quartz, and that has a very, very low CTE. So it doesn't change with temperature much, which gives you really stable focus. It's almost as stable as zero Dur, but has some advantages over zero Dur. So the first thing we do is we take it to our machine shop and we machine the mirror. We actually make the conical shape in the back. We put the raise the curvature in front. We put the core hole, and then it comes to the optic shop and we grind the mirror. So you grind the mirror, you polish the mirror, and then you figure it where you change it to the shape you want it to be. And then we test the mirror. And that's an iterative process. You figure test until you get the mirror to pass. And then we send the primary mirror out to be coated. And then it comes back and we mount it in our mirror cell. That's the way you hold the mirror. And then you test it. And this is where most people go wrong. It's not that hard if you have good metrology to make a good mirror. What's hard is to hold the mirror without ruining it. I mean, most of the time when you have telescopes with problems, it's because the mirror is being held and it's causing astigmatism, or it's usually astigmatism is what happens when a mirror is held poorly. So once it passes the test mounted and coated, right? So it should look just like the mirror did before. Then we go ahead and we start to assemble the telescope. And then once the telescope is all assembled, we test the completed telescope with a secondary mirror, M2 mirror, and the M2 mirror is uncoated, right? We put the whole thing in the test, and it either passes on the first try, or we see there's a zone or residual error, because all the minor errors in the mirrors, they all add up, and sometimes they add up enough to where you say, it doesn't quite pass. And so then we take out the secondary mirror and we do a little work on the secondary mirror to improve the system. And so once that's done, then we send, and it passes and meets our spec, then we go to, we send the secondary to be coated. And then when that's done, we get it back and we do the final assembly of the telescope, and then you test the telescope yet again. And now we test the complete telescope again to make sure it looked like it did back here and nothing strange happened. So every telescope at PlaneWave goes through the same process. It's like that many steps to make sure the system passes all the tests. I mean, every step. And the secondary mirrors have a similar path where they're being tested prior to getting here, and our lenses and everything. So once it's all done, we do the telescope final inspection. And final inspection means you put on the focuser it's shipping with, and if there's the dew heaters, you turn everything on, make sure the temperature sensors are all talking to the computer, like everything is checked, and then all taken apart, packed up, and crated and shipped. So that's sort of the process of what we go through to do a telescope. Now, a lot of other companies, they don't make their own mirrors, right? So they buy the mirrors, and they don't really have the ability to do the test of the final unit, and they don't have the ability, if there was an issue, to do anything about it. So we've become a very vertically integrated company, and we do most of the processes ourselves, so we have control. Here's an example of a 1 meter mirror being machined. So right now we're cutting the side off here, but it's 85 millimeters thick. Remember, there's a 120-pound mirror, and there's a bunch of lightweighting pockets in the back. And so this process, this thing gets machined. It takes about 200 hours to do this machining process, to do the back, do the core hole, and put the raise the curvature in it. Here's kind of the same shot of that being machined and some of the other machines in our machine shop. Here's a primary mirror that's been polished. This is like probably a 17. And you can see the little steps because you're seeing through the polished surface, front surface of the mirror to the back. And it's a conical shape. And to save time, because we machine every one of these, we do steps when we do the conical shape. And there's a 1 meter mirror that's just being ground, but you can see the light weighting pattern in it. And again, that's that 120-pound mirror. Other things we have developed at PlaneWave is custom optics machines. So these machines we've built. And actually the hardest thing for us to do was to make these, these tubs. We finally got good at the tubs, but we designed tub after tub, and surprisingly, of all the things, that was the biggest pain in the rear end. It's to try and make a good tub that doesn't leak, that's manufacturable. But we finally got it. And so here are the computer screen. These are computerized optics machines. They're controlled by the same drive system that drives the CDK 700. So we know how to talk to them really well. We know those motors intimately. And I think I have here's another close-up of one being polished. And they're neat machines because you can tell them, generally when you make a mirror, you polish for a while. But once you're done polishing, then you figure the center for a while, you figure the edge for a while. It's sort of a recipe. And so this thing will just go through and do the recipe, right? Let's say do this for 20 minutes and do this one for 60 minutes, then do this. And then it says, okay, come check it. So now the other part of making mirrors, when we saw the 42-inch mirror that we were making, we were doing, that I showed you in the last presentation, we were doing a knife edge test with a Coude mask. So it's called a Foucault test. And that's the way we tested the mirror. And it's a great way of testing mirrors, and but it only gives you a slice of the mirror, kind of what the profile of the mirror looks like in one slice. If you have astigmatism, coma, or non-symmetrical errors, you won't be able to see them. So now we test mirrors where we get a 2D profile, or even 3D, if you will. But so here's a profile, a wavefront that we get off the primary mirror. So every mirror is tested. You can see astigmatism is almost nothing, spherical is almost nothing, secondary, spherical, third order spherical, and trefoil, and Strel. We're, to be diffraction limited, we want the Strel to be over 0.8. But we always make the primary mirrors, better than 0.8, just because errors add up. You make two things that are 0.8, and then they have a couple errors, zones or something that touch each other, add up constructively, then you might knock your Strel down to 0.75 and not really be diffraction limited anymore. So we always go higher. And then you take, while you're testing, before you're done, right? Before it's good like this, it'll show there's errors. Well, here's one that shows errors, right? The red is high, the blue is low, and the green's kind of in the middle. And so what you do is we put this wavefront map into our optics machine, and then the optics machine goes, oh, okay, I'm going to work this area, this area, this area. You hit go, and it works all the areas, all the high spots, and smooths. And then there's a smoothing button you hit, and it'll smooth it. And then you test the mirror, and you do a couple iterations of that to finish your mirror. So this one is almost 0.8 Strel already, so it's getting closer. So we've developed over the years the metrology to do this optical testing, and then also these machines that read the optical testing and make our mirrors. Here's a 1 meter mirror in its optics machine, its polishing tub, and this one is being figured right now. And actually, when we're figuring the 1 meter mirror, it actually sits in the machine on top of the wiffle tree, the 18-point flotation cell, that the same style that's going to be in the telescope. That way, you're supporting it the same way in the machine as you'd be supporting it in the telescope, so it remains the same shape. Here are some mirrors that are mounted, coated mirrors that are mounted, and again, this is the big trick, right? Is to be able to hold a mirror without changing its shape. And that's where everyone makes the mistake. So this takes taken us, years to develop to this. I mean, we actually glue the mirror at multiple points in the center of mass of the mirror. So when you rotate it around relative to gravity, you don't induce any external torques on it. We have compliance here to allow the aluminum to expand and contract relative to the mirror, so you don't distort it with big temperature changes. And then the other nice thing about the way we mount the mirror is you don't collimate it. This thing has been pre-collimated. It will never move. The optical axis of this mirror is aligned to the mechanical axis of this backplate in this mirror cell and the whole rest of the telescope. So all you do is have to tip tilt the secondary to get the final collimation done. So it's a very stable, way to hold a mirror. And I think it's superior to any other way anyone else is holding a mirror in telescopes of this size. Here are some assembled optical tubes. And so these are doing final inspection. And in the final inspection, we actually check I was explaining that earlier. We test it with the electronics it's shipping with. You hook it up to the computer, you run everything and make sure if there's dew heaters, you make sure the heaters heat up and the temperature sensors read. Here's telescopes waiting for secondaries to come back from coating. So they've all been matched. They're all ready to go. They just need the coated secondaries to come back, and they get their final test, and they'll be ready to be created. Here is a horizontal test tunnel. So this is one of the places we test anywhere from the 12.5 to the 24-inch telescope. The complete optical tube gets tested in here. And then when we make the 700 and the 1 meter, there's an M3 mirror, a flat mirror that's like a diagonal mirror and shoots the light out the side. Those mirrors we get from another company that makes flats for us, and they're priced well, it's good material, it's the right material and everything, but they really just don't make them that well. So we get them and then we hand figure them and make them perfect. So this over here is a test setup for testing the M3 mirrors. And then here's a vertical test tower for testing the completed 700 and completed 1 meter telescopes. So this is a big, 1 meter flat. It's a little bit bigger than 1 meter, and it weighs like 900 pounds. It's held by an 18-point wiffle tree that's upside down and held by steel cables. So it's hanging there, but there is a little safety catch, so we're okay. And then when you get the final telescope, it too does this final test. And here is a 17. And you can see, I mean, it's got high spots and low spots, but we're talking, they're very small, so, and it's a 0.9 Strel. So really we get to these to about, 0.87, 0.88. We're, very happy for a complete system to be there. Just some other things. We also 3D print parts. So all our light baffles are 3D printed now, and that allows you to design much better shapes to catch light than you could before, when we used to make them out of aluminum tubes and try and put bafflets in there. And I mean, they used to be really labor intensive to make, and you can never make something as good as what we can do with a 3D printed. Plus the 3D print is a lot lighter weight. Yeah, so, and that extra weight puts stress on mirror cells and all sorts of things. So it's great to have a lightweight baffle. That has a really great shape to it. This is before it's painted. It gets a little sanding and then it gets painted ultra flat black. Okay, I'm gonna go over to like the mount assembly and L mounts and such. So one of the things we do is we make our own motors. We design and make our own motors. So this is the coils for the L350, our smallest L mount, and this is the coil winder for it. You put this, you jig this onto this jig, and it'll wind all the coils. And then for bigger ones, we wind the coils separately. The L500s, L600s, and also the 1 meter and the 700 motors are all wound on this. And here's some of the inventory in the L mount areas. You can see here's a bunch of the shafts that drive them, a bunch of the different plates. And here are wedges for mounting the L mounts. equatorially, so we have them in like 5-degree increments. Here are the weldments for the fork arms of different sizes. Here are coils already built up and ready to go into motors. Here's a motor being assembled for an L350. They actually both look like L350s. This is an L500 motor being put together. There's the neodymium magnets. Here's the encoder ring, and this over here is the read head that reads off this encoder ring, so we know our position. So here's some test bays for the L mount. So every L mount gets put in this test bay, hooked up to their own computer, and we run through a battery of tests, and we get a report in the end. But the tests, they do a tuning. They automatically tune it. They check all the different sensors, all the switches that are on there. They run them into every position. And we run them at really slow rates, fast rates, and it's a 24-hour test. So each mount goes through a 24-hour test, and in the end, you get this big test report and tells you if there's any problems. Here's kind of one of the test reports running one of the tests. And then so that's an L350, and these are two L500s. And then here is an L600. And the L600s, we actually, all those get tested with a 24 equatorially, because this is the hardest, there's a lot more of a cantilever here. So with the L600s, they all get mounted with a full load on them. We found that with the L500s, we didn't have to do it. Whether they're if they passed here, they always passed with the full load. L600s, you got to pass them with full load, otherwise, sometimes they could fool you. And this shows sort of the result. This is an L350, must be with a 14. And yeah, and so someone was asking about Altaz. So this is Altaz with the derotator going. And these are 9 images at 300 seconds each. So 9 5-minute images. And they're all unguided. And these are what the stars look like. I mean, here's a star kind of near the upper left corner. And it's a 2.25 arc-second star it's essentially perfectly round. And then here's in the center of the field, and you can't see it because this is in the way. Yeah, and so it was 2.28 arc-second stars and 3% aspect ratio. So I mean, very incredible performance. So this is all part of the dream. You're slowly achieving all the things we want telescopes to do. And, the 700 was the first step in that, the 1 meter was, and the L mounts are continuing that. It's all the things we learned from those being applied to these. So it's pretty neat. I think we already watched that. Yeah, this is the same video we saw before, so I'll skip that. And then I have a little bit on our larger telescopes. So here is a couple 1 meter telescopes. And this is how the mirror comes out. The mirror will, when you assemble it on site, the mirror is shipped in a separate crate. You would go ahead and install it here, roll this underneath, and then there's a lift that lifts it up inside, and then you bolt it in place. And here is 2 more 1 meters. And this one is actually going up to the Himalayas. So it's got, we had to add a bunch of heating elements to certain things because the temperatures are so cold that some electronics won't work at those temperatures. So we had to add a bunch of heating elements to that. Here is a new CDK 700. Actually, it's not a CDK, it's an RC 700, like an F11. But we designed this for NASA, and this is going to be used for laser communication. So they'll be talking to satellites and talking to, the next moon mission is what this is meant to talk to. So when the space capsule is going out there, not only will they communicate RF, but they will be communicating with a laser comm. So here's kind of a close-up of that telescope. You can see the wiffle tree, the electronics. I mean, there's a lot that goes on inside behind the primary mirror, behind the scenes. But this 700 will also have a mirror that slides out and gets put into place. And it's also, the 700 is a lightweighted mirror, just like the 1 meter. And here's a video showing the 1 meter moving at 50 degrees per second, so you can kind of see. And that's me talking in the video, but I'll walk up there to kind of show you the size. Anyways, so and I think that is what I have for that. How are we doing on time?
No, we're fine on time.
Great.
Great. Did you want to take a couple of the questions on that section?
Absolutely. Let's do it.
Okay. David Kelshow, does direct drive still have stepping during high power? I guess it's high magnification power.
No, no, it's not. It's not like a stepper motor. It is a it's a 3-phase synchronous. You can actually hold it into any position to the accuracy of the encoders, and the encoder accuracy is better than 1/10 of an arc second. So it's, in fact, on the 1 meter, it's even a lot less than that. But you need it to be about 1/10 of an arc second. But it's nothing like a stepper motor.
So I'll interject a question before Dean's. Earlier you were mentioning unguided. Do you ever need to guide your scopes?
Sure. I mean, you can do, if you do 5-minute unguided, you get like, 80-90% of the images are perfect for astrophotography. Astrophotography is actually the hardest almost, because, if you have 0.4 arc seconds of drift, the stars start to look a little elongated, assuming the scene is pretty good, and so if you get about 10% elongation, you start to notice it, and it doesn't look very good. So, anyways, if you take longer than, you can take, I've seen 30-minute images that are perfect, but you're not going to get every 30-minute image perfect. So if you're taking 20, 30-minute images, usually you guide just to make sure, because you invested that much time.
Okay. Let's see. Dean Kettleson has perhaps a little bit more involved question about your testing technique and fringe mapping, null testing, phase shifting.
Well, we do a proprietary test, but it's really it's like a Hartman test. But the real trick is the algorithm that analyzes and turns it into a 2D wavefront map. And we've tested against interferometers like, a lot. So we have the advantage to our test is that we can do it quickly. You can do a test in 5-10 minutes, where interferometry takes a long time to set up, and it's very expensive, and you can have one of them usually. For a company our size, we might be able to have one interferometer, but we've got like 10, 15 test stations. We can add them whenever we want, and we check against, like we had 4D out recently, and tested one of our 20-inch telescopes, a completed telescope, and compared it to our testing. And we do that quite often, just to check and see. And the nice thing is we can even check optics under the sky. We can check a finished telescope, and we can check primary mirrors. So.
Maybe to add on to Dean's question, when you had the fringe measurement in the tubs, I think it was in the tubs, and you had some high spots or low spots, would you have to tell the computer which area to work on, or does it just know based on the specs?
No, it looks, so it looks at the image and figures out where it's going to work. And although it will keep over and over, we still stop when we say it's done. The computer would So it's an iterative process. You run, you see, it'll say, I'm going to work these high spots for this amount of time, which is usually a little less than probably, you don't want to nail it the first time because you can overshoot. And it will complete that run. You test it, it's a 5-minute test, and you go, you put the new wavefront map in, it'll do the next one. It'll just keep rubbing on the high spots. Even if they're only 1/10 of a wave high, it'll try and fix them. It stops working at about 1/10 of a wave. You know, I mean,
Yeah, right. Okay.
you just start moving around spots then.
Alrighty, and David had a follow-up question. Do the scopes come with a computer or software?
They come with software, yes.
Okay.
They don't come with computer because we with even L mounts had thought about putting a computer in them, but ultimately we don't want to be responsible for computers, and people have opinions about their computers. So we didn't want to be a computer company, you know. But definitely software. They got to come with the software, and it's free. Comes with the telescope.
Okay, so maybe he was also asked, I don't know, maybe I'll expand his question. Location-wise, would you enter your own location from your own GPS coordinates and all that?
Oh, well, so if you have internet, you can go to Google Maps, pick out where you are, and put it in that way. You do when you're setting up, you do enter a location. So you either enter it because you look on a GPS. We do have on the 700s in 1 meters away that the GPS can talk to it, but I don't think that's not really implemented on L mounts at this point. But it's really not used very often. Most people are mounting these permanently, and it's a one-time thing. So
right, yeah, good point.
And usually they have internet, so Google Maps is a great way. You go, I'm right here, and it'll put in your longitude and latitude.
So yeah, I've got a practical question. Like out here in Arizona, we've got a lot of dust, and you know the dome's open. So what kind of maintenance schedule do you recommend for your scopes?
Well, I mean, you like to clean mirrors not too often, like where you're physically touching them. So generally, you know, if it's dust, you try and blow off the dust as much as, you know, you can do that regularly. You can also use like a snow gun pretty regularly, which is a CO2. That's what like New Mexico Skies does. They'll go out and clean the mirrors that way. But a little bit of dirt isn't really a problem. So I'd say you clean it once a year unless you really have something going on. If it doesn't blow off and you got pollen, sometimes that happens. You know, and then we've got a procedure for how to clean that.
Yeah, I guess I was wondering also about the drive and the gears and that sort of stuff. It's completely enclosed, or?
Yeah, like the direct drive is the only pieces that are touching is the bearing, and the bearing is sealed. So that's the part that touches and moves. Otherwise, you know, you're actually sitting on a motor. The bearing and motor are all kind of built together. So the only moving part, the part that could wear out, is the bearing, and we don't come close to using the bearings up to what they're designed to do. You know, they're designed to be on motors that are spinning for, you know, years, and you know, so we're barely moving them compared to what they're used to. So the L mounts really last a long time, and there's no gears to wear out.
Okay. And another comment, what's next? What do you still want to improve? What would you do if you, what's your ultimate dream scope?
Well, we've got some things. Well, I've got one thing that I'm going to show you here after this. And then I think we're also working, we started working on a 2-meter telescope. And I'll tell you, 2-meter telescope is huge. It dwarfs the 1 meter. It won't even fit in the building that we have there. So it involves new buildings, new machines, new testing, all the tooling, and new machines to even machine the glass. So, but we're talking to you know, 5 or 6 potential customers for that.
Okay. And let's see, does your software have a pointing model built in, or how does one do that?
Yes, it does. Yeah, we've got Point XP. I had a video. I just didn't want to bore you with it. Where we're doing. I have a short video that shows us making a mount model. You know, and
Oh,
it takes the image, does a plate solve. It's our own plate solve. We have our own focus software, which if anyone uses our focus software, they all want to move over to our focus software. So now ACP has a driver for it, and CCDAP has a driver for our focuser now. It's focusing software, because it's our focusing software will move the focuser, take an image, then move focuser, take an image, move focuser, take an image, take like 5 images. And then it looks at the average RMS diameters of the stars in all the field, is across your whole field. So and then gives you a V curve. So it's not like looking at one star, it's looking at your whole field. And it can also tell you if the field's tilted, or if if this side is focusing higher than this side is. So we use it to, we used it in the beginning when we were making the 24. We designed the focusing software just to measure field tilt. That's why we designed it. And we're like, God, this is the best focusing software I've ever used. So we started using it on our stuff. And once people discovered it, they started, wanting to be able to use it too.
okay, nice. And the last one, do the mirrors have covers?
We do have covers. I think it's an option, because covers, have motors and we have it ships with covers that you put on yourself, but we also have some automated covers if you desire that.
Okay, I think that's the last of the batch for that section. So if you'd like to continue,
All right.
please do.
Very good. Let's see. So, a new product we're working on and have been playing with lately is a new 14-inch telescope, or 350 millimeter telescope, just under 14 inches. And it's an F3 telescope with, it's an F3 telescope with a 3-degree field of view for a 60 millimeter imaging circle. It's Cassegrain. It's a fixed primary and secondary, so it stays collimated really well. And it has dew heaters and temperature sensors and all the other features our telescopes have. Here's the delta row on the L350. Here's sort of spot diagrams, and this is a portable pier that we also sell for specialty clients, but it's a pretty cool thing. So we roll it out on that pier and test. Here's sort of the layout of it. It's a big secondary mirror. It's a pretty fast primary mirror. And there's 3 lenses and the camera here. That's sort of the mechanical design. So here's a nice, it has fans that blow across the primary mirror. It has fans that blow around the back of the primary mirror. And it's just a really fast, high étendue telescope. Let's see, another view of it. The lenses actually stick out a little bit here. So our focuser, I'm showing the pictures here with our regular focuser rotator, the IRF90, but it actually is coming with a new focuser. Oh, this is another kind of mount more for commercial companies. But that's kind of a neat thing, showing 4 of these delta rows. Some people we were talking to. Anyways, what was I looking for? Oh, here's a nice view of the cutaway. And again, 3D printed baffles. So again, you can have these nice light traps. It works really well. We've had it very close to very bright stars, and the baffling is really good. Even like did some tests, you shoot the horse head and there's always like bright stars nearby. Zeta Orionis is always going across your field. This is baffled really well, very dead. And there's also a new focuser and rotator for this, and it's low profile. These will also be available for our CDK 700 and our other telescopes, all our telescopes. So, and the nice thing is the rotator is much faster than our current rotator, and the whole profile cuts down about 1/2 an inch on the overall back focus used by our current IRF 90. And so here it kind of shows them stacked up together and the amount of back focus you have and how much they use. So, and here's like a test shot. This was like, I think it was 122nd shot of the, just drew blank, wait, don't tell me. It's the, why am I having a trouble? Somebody tell me. It's the Rosette, thank you, Rosette. Yeah, just, I kept saying Triffitt, no, not Triffitt, Rosette, thank you. And so here's a test shot of the Rosette. And you see a great field, pinpoint stars all across the field. Here was sort of the test setup that was being used. Before we had the carbon fiber tubes in stock, we used a white tube. Here's kind of a first color image. We're just starting to take images on it. This is going to be something that's available in the summer. And it's just under $16,000. So it's a nice F3 portable, really fast astrophotography telescope that we're really excited about. And I think that's what I got for you.
Cool. Thank you very much. So I guess one question in general is what's the lead time on some of your instruments?
Well, we try and keep it to 3 months or less. I would say right now it's a little bit, it's been a busy beginning of the year, so we're a little bit longer than that. But we're trying really hard to, with the new optics machines, we're pumping out optics much faster than we ever have before. And so we'll get our lead times back down to 3 months. It's generally around 3 months.
That's not too bad.
Yeah.
Yeah. One question was, what's the weight of the Delta Rho 350?
Let's see. I think it was about. It's about 50 pounds, or it seems heavy to me. It doesn't sound right. I think I just saw that. I would say it's probably around 40 pounds. I saw 50 somewhere, but there's no way that's right. It's lighter than that. So probably around 40 pounds.
Okay, that's not bad either. Let's see. Any other Q&As? Last chance for the last question. You just wanted to pop in, but didn't get it in there. Covers with mount?
Covers with mount.
Not more detail, David?
Like, can we put a cover over the mount, maybe? I'm not sure.
Oh, comes with mount.
Oh, no. The mount is separate. So it's the optical tube is sold separately. You can buy, that's a package that would be sold. But this telescope would also, a lot of people have, software bisque mounts, or, it would, works well on, I imagine if you already have a mount, you're not going to want to buy another one. So.
Okay.
So we'll sell a lot of packages, but we'll also sell the OTA by itself.
And what would the mount cost to go with that?
The mount is $10,000. So this setup is about 26, right? Yeah, about 26,000.
Okay, thank you. I think that took care of that one. Oh, so I've got one question. If I had my dream scope, I would like to have adaptive optics. Have you ever Have you explored the thought of maybe someday?
You know, we've talked a lot about adaptive optics, but it has issues. We actually have some ideas. We're doing, uh, we have some ideas of maybe how to solve that problem a different way. But the problem with adaptive optics is you need a bright star, um, and um, and it doesn't cover a wide field of view. So it covers
Hmm.
a small field of view. It stops working. You know, if you have a nice half-degree field of view or 20 arc minute field of view, I mean, it doesn't even cover that. It really is an on-axis uh, thing. So in the end, it just isn't very practical. We thought about with big optics using adaptive optics to, uh, you know, like you image over here, and if there's flexures and things in the mirror, you have adaptive optics fit that just for right there and have the most optimal optical system you could have, you know. But you know, like I wouldn't really help our 1 meter much, which because it stays in shape pretty well. So I don't know. We're working with some adaptive optics companies, but their market is going to be more people doing laser comm and doing, you know, narrow field stuff.
Okay, so maybe when you get that 2 meter scope out there, you might.
Right. But I think there might be some possibility with the new CMOS cameras. There may be some things.
Mm.
Dave Rowe's working on some fun concepts that could, you know, might improve, kind of act like adaptive, give you improved images. So
Okay, well, thank you.
algorithm intensive, and but
Okay, I think that should wrap it up. Thank you very much for wonderful talk, and I think people will have some wish lists for their Christmas presents.
I hope so.
Dreams. Yep. So, Gordon, do you want to come back on?
All right, let's see. Yeah, there I am. All right, now Rick, we all look at plane waves in awe, and even though you're still way up there, thanks for bringing it down a notch or two, explaining what this is about and the processes and the manufacturing and how you have brought these fantastic instruments to the general public and to us amateur astronomers. You are the man, and the company is the company. That's for sure.
Well, thank you. I mean, someone asked, what is our dream? And I said the 2 meter. There's also a dream that we have to have something finally portable. That would be really fun because all our telescopes are not very portable. I mean, I would like one that when I'm out with the family, I can pull out. It's most of the best things we design are things we wish existed. So that's something I wish existed too.
All right.
We were talking about it all the time. So.
Oh, good. Well, certainly with your innovation and constantly changing and bringing new products, that anyone interested at all, they need to keep up with your company because it certainly is dynamic.
Oh, well, thank you very much. And it's
thank
great.
you.
It's great talking to all of you, and thanks for being interested in having me out here. And be fun to see you guys in person again and see you at SAS, and you know that'll be great.
Good. Great. Thank you for that very very special and unique presentation. We appreciate that. So let's see. There was another question that came on. Oh, nope, that was a thank you. And let's see, another chat. Anything in the chats? Nope. Nope. Asking about what the website is. That's in the chat. If anyone is interested in the Astronomical Sciences Conference chat. So I think that will do it. Remember, everybody, that next month our meeting is kind of late in the month. The third Friday is the 21st of May, and Dave Eicher will be there, the editor of Astronomy Magazine, talking about star cities. So again, you know, we're bringing, obviously, guys, we are bringing top-level people, as Rick certainly attests to, and next meeting certainly will keep that level of professional astronomy folks.
Dave Eicher's the man.
Oh yeah, okay.
Yeah, he's a great guy and great presenter.
Yeah, good, good. We all read about him, so now we get to see him.
Yeah, yeah, he's good.
Yeah, good. So everybody, be sure to jump in during our main meeting and meet Dave. That's all that I have. Tom, is there any last minute things from you?
Nothing on my end.
Okay, and Rick, anything you want to add in?
No, I think I'm good. Again, it's been a pleasure, guys.
Okay, and
Very
Bob, I'll give you a last chance.
No, Rick, thanks very much. It's really impressive, the innovative design, manufacturing technology, and quality management all integrated. Fabulous instruments, wonderful company.
It's a great team of people. That's what makes it happen.
Okay,
Thanks.
good, good. Okay, folks, I will give the usual countdown. So anyone can jump on in, and we'll close on down during my countdown. So 3, 2, 1. Bye, everybody.
Bye.